Hi dear students, we have completed the two modules and today we start the third module, that is the transient currents. Okay, that is in this module we discuss how the current and voltage grows or decays in a circuit that containing resistor, capacitor and inductor when the circuit is switched on or off. That is, in this chapter we will discuss the growth and decay of the current, the circuit containing resistance, inductor and a voltage source, and also the circuit that contains capacitor, resistor and a voltage. Okay, when the switch is just pressed, a current starts to flow through the circuit for a certain time, and then the current will become stable. And also when the circuit is broken, that is when the key is opened, the steady current that start to decrease and it finally goes to zero. This is the growth and decaying of the current in the circuit. Here, as I mentioned, throughout this module, that is, we will discuss how this current and voltage grows or decays in the circuit when the circuit is just switched on or off. Fine. Now, what is the term transient current means? Transient current means it's an oscillatory or periodic current that flows in a circuit for a short time. അതായത് നമ്മുടെ ഒരു സർക്യൂട്ട് കണ്ടെയ്നിങ് resistor and inductor, also key. ഈ key just press ചെയ്യുമ്പോൾ, when the key is just pressed or the key is just closed, the current starts to grow through the circuit. That after a certain milliseconds, the current grows and reaches a saturated value. After that, a constant current flow through the circuit. Okay. Then the transient current means this is an oscillatory or periodic current that flows in the circuit for a short time. That is, when the key is just pressed, the current that start to grow very slowly, that means its magnitude slowly rises and increases, then and reaches a steady value. Then if a steady current is flowing through the circuit, then if I just open the key or I break the circuit, then the current decreases and reaches a zero value. That is, the transient current is a current before reaching the steady state. That is, in a steady state, the current and voltage becomes constant, but in transient state, they changes and tends to become a constant. But transient current എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ സ്വിച്ച് ഓൺ ചെയ്തതിന് ശേഷം കറണ്ട് ഇങ്ങനെ ഇൻക്രീസ് ചെയ്ത് അതിൻ്റെ മാക്സിമം എത്തുന്ന ഒരു വാല്യൂ. ഉദാഹരണമായിട്ട് ഈ ബാറ്ററി ഇതിൽ സപ്ലൈ ചെയ്യാൻ പറ്റാവുന്ന കറണ്ട് ഒരു 10 ആംപിയർ കറണ്ട് ആണെങ്കിൽ ജസ്റ്റ് കീ അങ്ങ് പ്രസ് ചെയ്ത് കഴിഞ്ഞാൽ ടൈം t is equal to 0 ആകുമ്പോൾ ഇതിലൂടെ ഒഴുകുന്ന കറണ്ട് I is equal to 0. ടൈം t is equal to 1 millisecond. റഫ്ലി ഞാനൊരു എക്സാമ്പിൾ പറയാണ്. കറണ്ട് പതുക്കെ കൂടും, 1 മില്ലി ആംപിയർ കറണ്ട്. അങ്ങനെ ഈ 10 ആംപിയർ കറണ്ട് എത്തണമെങ്കിൽ ഒരു ടൈം is equal to 10 millisecond ഓക്കെ ആവുമായിരിക്കും. അങ്ങനെ ഒരു 10 millisecond ടൈം കഴിഞ്ഞാൽ പിന്നെ ഇതിലൂടെ ഒഴുകുന്ന കറണ്ട് 10 ആംപിയർ കറണ്ട് ആയിരിക്കും. അപ്പം ട്രാൻഷ്യൻ്റ് കറണ്ട് എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ ഈ കറണ്ടാണ്. അതായത് സീറോയിൽ നിന്നും അതിൻ്റെ കോൺസ്റ്റൻറ്റ് വാല്യൂയിലേക്ക് എത്തുന്നതിന് മുമ്പുള്ള ആ കറണ്ടാണ്, അത് ചേഞ്ചിങ് കറണ്ടാണ് ശരിക്കും ട്രാൻഷ്യൻ്റ് കറണ്ട് എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ. അതേപോലെ തന്നെ നമ്മൾ കീ അങ്ങ് ഓപ്പൺ ചെയ്ത് കഴിഞ്ഞാൽ, സർക്യൂട്ട് ബ്രേക്ക് ആയി കഴിഞ്ഞാൽ, ഈ മാക്സിമം 10 ആംപിയർ കറണ്ടിൽ നിന്നും കറണ്ട് പതുക്കെ ഡ്രോപ്പ് ചെയ്ത് 0 ആംപിയറിലേക്ക് എത്തും. ആ കറണ്ടും ഡീകേ കറണ്ട് എന്ന് പറയും. നേരത്തെ കേസിൽ കീ പ്രസ് ചെയ്തപ്പോഴുള്ള കറണ്ട് ഗ്രോത്ത് ഓഫ് ദ കറണ്ട്, കീ ഓപ്പൺ ചെയ്തപ്പോഴുള്ള കറണ്ട് ഡിക്രീസ് ചെയ്ത് 0 ആകുമ്പോഴുള്ള കറണ്ട്, അതും ട്രാൻഷ്യൻ്റ് കറണ്ടാണ്. ദാറ്റ് ബി കോൾഡ് ആസ് എ ഡീകേ കറണ്ട്, ഡീക്കേയിങ് ഓഫ് ദ കറണ്ട് ഇൻ ദ സർക്യൂട്ട്. ഇതിനാണ്, ഈ കറണ്ടിനെയാണ്, ഗ്രോത്ത് ചെയ്യുന്ന ഈ കറണ്ട്, ഡീകേ ചെയ്യുന്ന ഈ കറണ്ട്, ആ ഒരു കറണ്ടിനെയാണ്, ചേഞ്ചിങ് കറണ്ടിനെയാണ് നമ്മൾ ട്രാൻഷ്യൻ്റ് കറണ്ട് എന്ന് പറയുന്നത്. ഓക്കെ, ദാറ്റ് ഈസ് the transient current can also be interpreted like this. It is a current that is flowing through the circuit before reaching a steady state. സ്റ്റഡി ആയിട്ടുള്ള കറണ്ട് സർക്യൂട്ടിൽ ആവുന്നതിന് മുമ്പ് അതിൽ കൂടി ഫ്ലോ ചെയ്തുകൊണ്ടിരിക്കുന്ന കറണ്ടാണ് ട്രാൻഷ്യൻ്റ് കറണ്ട്. Then after reaching the steady state, that is in steady state, the current and voltage become constant. Okay, but in the transient state, they change and tend to become a constant. Okay, അതാണ് നമ്മുടെ ട്രാൻഷ്യൻ്റ് പീരീഡ് എന്നൊക്കെ പറയാറില്ലേ. ആ ട്രാൻഷ്യൻ്റ് സീറോയിൽ നിന്ന് മാക്സിമത്തിലേക്ക് സ്റ്റഡി ആവുന്നതിന് മുമ്പുള്ള ആ ഒരു ട്രാൻസിഷൻ, ഒരു ട്രാൻഷ്യൻ്റ് സ്റ്റേറ്റിനാണ് നമ്മൾ, ട്രാൻഷ്യൻ്റ് സ്റ്റേറ്റിലുള്ള കറണ്ടിനാണ് നമ്മൾ ട്രാൻഷ്യൻ്റ് കറണ്ട് എന്ന് പറയാം. Okay, now let us goes to the first topic in this module, that is the growth and decay of current in an LR circuit. The growth and decay of current in inductor resistor circuit. The circuit containing the inductor and a resistor. That is, this is a circuit containing resistance and an inductance L. So growth means just the key is pressed, small amount of current starts to grow in the circuit. Okay, before reaching the steady state, whatever the current is flowing through the circuit, that is a transient current. Then here first we discuss the growth of current in the LR circuit. Here we will derive an equation for the growth of the current in the circuit. That expression will be in terms of the resistance L and the inductance L. Okay, that is, just when the key is K is closed, a current I starts to flow through this circuit. As I mentioned earlier, when the key is just pressed, the current starts to increase. The current grows very slowly. That the current flowing through the resistance and the inductance increases or grows very slowly. If there is a rate of change of current, that is di by dt in the circuit, then the flux through the coil changes. Because of the increase of the current and due to the increasing the flux, a self EMF will be induced in this coil. That self EMF developed across the inductor opposes the applied EMF. Okay, the EMF induced across this inductor, that is written as L di by dt. That is a voltage developed across the inductor. V is equal to L di by dt. അതായത് നിങ്ങൾ പഠിച്ചിട്ടുണ്ടാവും, ഈ സർക്യൂട്ടിലെ കറണ്ട് ഇങ്ങനെ പതുക്കെ ഇൻക്രീസ് ചെയ്ത് വരുമ്പോൾ കറണ്ടിൻ്റെ മാഗ്നിറ്റ്യൂഡ് സീറോയിൽ നിന്നും അതിൻ്റെ മാക്സിമം വാല്യൂയിലേക്ക് എത്തുമ്പോൾ കറണ്ട് വേരിയേഷൻ ഉണ്ടാകുമ്പോൾ ഇവിടെ ഒരു ഫ്ലക്സ് ചേഞ്ച് ഉണ്ടാവും. ആ ഫ്ലക്സ് ചേഞ്ച് കറണ്ട് ഇൻക്രീസ് ചെയ്യുമ്പോൾ ഒരു ഫ്ലക്സ് ചേഞ്ച് ഉണ്ടാവും. ആ ഫ്ലക്സ് ചേഞ്ചിനെ ഓപ്പോസ് ചെയ്യുന്ന രൂപത്തിൽ ഒരു ഇ എം എഫ് ഈ ഇൻഡക്ടറിൽ ഡെവലപ്പ് ചെയ്യും. ആ ഇ എം എഫിന് നമ്മൾ പറയാം ഇൻഡ്യൂസ്ഡ് ഇ എം എഫ് എന്ന് പറയും. ദാറ്റ് ഇൻഡ്യൂസ്ഡ് ഇ എം എഫ് ഓപ്പോസസ് ദ അപ്ലൈഡ് ഇ എം എഫ്. That is the story here. That is, I have written here, when the key is just closed, a current I starts to flow in the circuit. That current is I, this I. Okay, that is here that is why the title is growth of the current. While the decay of the current, what we will do is, after a steady current is flowing through the circuit, just we open the key or we break the circuit. That time also a current from the maximum starts to decrease and reaches zero. That is the decaying of the current that we will discuss later. Here we are talking about the growth of the current. Then if a current I increases through the coil, then the flux through the coil increases. Then the coil tries to opposes the increase of the flux, or the coil tries to opposes the changing flux. That is a back EMF that will be developed. That is, we will say a self-induced EMF. This minus L di by dt develops across the inductance, and that self-induced EMF opposes the applied EMF. Therefore, here I will write the voltage developed across this self-inductance is L di by dt. That is the magnitude of the induced EMF is L di by dt. Here the minus sign shows that the induced EMF is just opposes the applied EMF E. Okay, where the E means this is the voltage supplied to this circuit by an external agency. This is an externally applied voltage. This is simply we can say this is the applied voltage. Fine. Now we have to write the equations of the voltage. That is how we can apply, how we can write the equations of the voltage in the circuit. That I have discussed in another video. For better explanation, you see that video. That is, I consider a path along this direction. Then we can write the Kirchhoff's voltage law equation. That is, along the path, if I come along the path, I will see the negative terminal of the battery first. Therefore, this is minus E. Then, while coming, I meet the resistor, and the direction of the current, that is along the direction of the path we have taken. Therefore, the path and the direction of current both are along the same direction. Therefore, I will take positive sign plus IR. Then the EMF induced across the inductor L, that is plus L di by dt. There is no other source, voltage source in the circuit. Therefore, this is equal to 0. This is a way of writing the voltage equation of a given circuit. If I rearrange the term, I can write this is as a E is equal to IR plus L di by dt. I put this is equation 1. Then, as I mentioned, in the circuit, the current starts to flow just after the key is pressed. That is, at time t is equal to 0, our current is equal to 0. Time t is equal to 1 millisecond, current I is equal to 1 milliampere, roughly. In this way, as time goes on, the current increases and the current reaches the maximum value. If this battery can provide, or if the battery can generate total maximum current 10 ampere, then after a certain interval of time, maybe time t is equal to 1 second, 10 ampere current will be there in the circuit. This is the steady current. Okay. There is, I can write here, after a short time, the current will become steady. That is, a steady current means our I will become I0. I represent the steady current as I0. Then if the current is steady, there will not be any increase or decrease of the current. Then here this di by dt, that will be equals to 0. Okay, that is, I will write here di by dt will be equal to 0. Or from the equation 1, I can write E will be equal to, I can write instead of small I, capital I0 R. If di by dt is equal to 0, equation 1 reduces to this form. Or the maximum current that is flowing through the circuit is equal to E by R. Actually, here what we are going to do, our attempt is to develop an equation for the growth of the current in the circuit. After a certain time, how much current will flow through the circuit. We will develop that equation in terms of the resistance and the inductance value. Okay, if I substitute these changes into the equation 1, that is, instead of E, I can substitute this value here. Therefore, equation 1, that can be written as I0R is equal to IR plus L di by dt. That is, I bring this term to left hand side. There is I0 R minus IR is equal to L di by dt. Then if I take R outside, it is I0 minus I is equal to L di by dt. I can rearrange the terms here. I bring the L left side, R by L dt is equal to di by, I bring I0 minus I right side. Then if I do the integration, then both side, here I will get, that is, okay, I will do the integration, integrate di by R0 minus I, and the integration will give you minus natural log I0 minus I. Here this will be R by L, integration of dt will be t plus c. Fine. Where c is the constant of the integration. Constant of integration. Okay, now we have to find what is the value of c. For this, I will do the calculation here. That is, to find c, put time t is equal to 0. Constant of integration initial condition apply. We always apply the initial conditions to find out the constant of the integration. That is, at the time t is equal to 0, no current is flowing through the circuit, therefore I is equal to 0. Then put all these values to this expression. Therefore, the left hand side will be, sorry, the right hand side, natural log I0, because this I is equal to 0 at time t is equal to 0. Then the left hand side of this equation, that will be time t is equal to 0, this term is 0, then the remaining term is C. That is, C is nothing but minus natural log I0. Then put this value into this expression. Okay, we will get minus natural log I0 minus I is equal to R by L T minus natural log I0. Instead of C, I substituted minus natural log I0. If I multiply with the minus sign, then this will be natural log I0 minus I is equal to natural log I0 minus R by L T. This here I multiplied with minus 1. Or I can write this equation in this way. That is, natural log I0 minus I is equal to minus R by L T plus natural log I0. Here I bring this I0 term, natural log I0, to the left side. This will be natural log I0 minus I by I0. Goes to the left hand side, it will be minus natural log 0. Then I can take it into the denominator. This is equal to minus R by L T. That is, if I do the integration, this will be I0 minus I by I0 is equal to e power minus R by L T, or this can be written as I0 minus I is equal to I0 e power minus RL by T. We were looking at an expression for the current. The current term is here. I can keep this current in one side and take all other terms to right side. That is, I0 minus I0 e power minus RL by T, that is equal to I. Or this I can be written as I0 into 1 minus e power minus R by L T. Okay. This is the expression for the growth of the current in an LR circuit. This is the equation for growth of current at any instant of time in LR circuit. This equation is also called Helmholtz equation. Okay. Now let us define a new quantity, that is tau. Tau is equal to L by R. That is, here we have the quantity R by L. That is, the new defined quantity is tau is equal to L by R. This is nothing but the relaxation time. Okay, we will come to the definition of the relaxation time later. Now I can write this expression in terms of the relaxation time. That is, I is equal to I0 into 1 minus e power minus t by tau. Now when the time t is equal to tau, this equation I will become I0 into 1 minus e power minus 1, because tau by tau will be cancelled out. Or this can be written as I0 into 1 minus 1 by e. What is the value of 1 by e? I0 into 1 minus 1 by e means 0.3679. That is the value of this 1 by e. Therefore, I will write this expression. If I subtract 1 minus 0.3679, this will be 0.6321, or I will write this I is equal to 63.21% of I0. This is nothing but percentage. Or we can say I is equal to 0.6321 I0. Okay. There is the relaxation time. This tau can be defined as, this is the time required for the current to reach 63.21% of its steady value. I0 is a steady value. Then the relaxation time of the circuit is defined as the time required for the current to reach the 63.21% of the steady value. Let me note down, that is a relaxation time of the circuit There is a relaxation time of the circuit can be defined as the time required for the current to reach 63.21% of its steady value. Okay, let us plot this equation. That is the plot of current, that is the growth of the current in the circuit that we obtained is minus e t by tau. Then to plot this equation, let me check these values. That is, when t is equal to tau, what will be our steady current? That is, just now we have seen when t is equal to tau, this will be 0.6321 I0. When time t is equal to 0, what about this current will become? T is equal to 0 means this term will be 1, then 1 minus 1, our equation, this will be I0 into 1 minus 1, it is nothing but 0. Then time t is equal to infinity, then what about this term? I will be I0 into 1 minus e power minus infinity. This e power minus infinity is nothing but 0. Therefore, this is equal to I0. That is, if you look at this one, when the time goes to infinity, the current in the circuit reaches its maximum value, that is I0. It means it takes infinite time to reach its steady value. That is, theoretically, the current never attains the steady value by continually approach. See, this theoretical calculation, that is, this shows that the circuit takes infinite amount of time to reach the steady value of the current in the circuit. That is, theoretically, the current never attains the steady value. Okay. But practically, the L is very much less than R. That is, the value of the inductance used will be in the very small compared to the magnitude of the resistance value. That is, usually we use the inductance value like a millihenry. The resistance we will use in the like a kilo ohm or at least 2 ohms. Therefore, the relaxation time that will be defined as tau is equal to L by R, that will be very much less than 1. If L is very much less than R, the ratio L by R will be very much less than 1. Or if I take this quantity as X, which quantity? That is in the expression, that is I is equal to I0 into e power minus t by tau. I take this quantity, that is t by tau as a X, then this expression will be I is equal to I0 into e minus e power X. That is, when the time tends to infinity, that is X is equal to t by tau, that will tends to infinity. That is, our X tends to infinity. Therefore, e power minus X means e power minus infinity, that is nothing but the 0. That is, this goes to minus infinity and this term goes to 0. Therefore, our e power term goes to minus infinity, this will be 0. Therefore, the expression for the current, that will be equal to I is equal to I0 into 1 minus 0, that is equal to I0. That is what is the meaning of this calculation? That is I is equal to I0. That is, the current in the circuit reaches its steady value in a fraction of a second. That is I is equal to current in the circuit reaches its steady value in a fraction of second. Then from these calculations that we have done here, and in addition to this, we will do some other calculations also. That is, when time t is equal to 2 tau, the value of the current I will be I0 into 1 minus e power minus 2, because here when we substitute, instead of t 2 tau, this tau and tau will cancel, then this will be e power minus 2. Then if I substitute the value of e power minus 2, this will be I0 into 1 minus 0.135, this will be equal to 0.865 I0. Fine. Now, if you consider all these values, this time, if you plot the time on the x-axis and the current on the y-axis, then what will be the plot? That is, on the x-axis, this is the time in millisecond, and on the y-axis we have the current I, and this is the maximum steady value of the current. Then at a time t is equal to 0, that is this value, current I is equal to 0, that is this starting point. When current t is equal to tau, if I here denote tau, 2 tau, 3 tau, like this, then time t is equal to tau, this is 0.6331 of the, this is I0 value, then this will be half around this, means around the point will be here, and goes on when the time 2 is equal to 2 tau, this is a 0.865 I0, that is this is a tau, this is a 2 tau, this is 3 tau, and this will be very near to 0.8, means somewhere else here roughly. If you plot this graph, this will be approximately, it will go in this fashion. This is the plot of the growth of current in LR circuit. Growth of current in LR circuit. Here we have one note here, that is if L by R is larger, because we have already defined this tau is nothing but L by R, then tau is larger. If tau is larger, longer is the time taken to reach its maximum value. This is all about the growth of the current in an LR circuit. Okay, thank you very much.